Hello everyone, how's it going? My name is Dan the Tutor. Today we are going to be talking about 2D momentum problems. And honestly, if you know regular momentum, 2D momentum is not that bad, as long as you're also good at sine and cosine, breaking up things into components, that sort of stuff. So first let's review regular momentum. You would say momentum P equals mass times velocity, and we have that conservation of momentum equation, P initial equals P final. Great. So now the only thing we're going to add to this with 2D momentum is I need to say P initial in the x equals P final in the x, and P initial in the y equals P final in the y. I'm pretty sure that's straightforward. And remember that a lot of times you have more than one thing you're adding together for any one of these, and we'll explain what I mean by that in some problems coming up. The other thing we need to know is that if you have some vector in this class that points at an angle, like 20 degrees, and let's say this is 30, then you need to know that if you want to find the x and the y components, you construct a right triangle, and then you would say sine of 20 degrees equals opposite over hypotenuse, so y over 30, which means that y equals 30 sine 20. And if you do the same thing with cosine, you'll eventually get x equals 30 cosine 20. Now remember that it's not always cosine is x, sine is y. It's because sine is the opposite leg and cosine is the adjacent. I could just as easily give you not the 20 degree angle, but I could give you the 70 degree angle here, and now everything flip-flopped in terms of x and y. So you do have to be careful of that. So assuming we're good with all of this introductory information, let's look at two problems today. The first question I have is, let's say you're playing pool. Pool's a fun game. And this is going to be a top-down view of the balls that we're looking at here. So here's the 8 ball, here's the cue ball, which is the white ball that you hit with the pool stick. Let's say they both have a mass of about 1 kilogram, so same mass, 1 kilogram. And you are going to strike the cue ball with a velocity of 5 meters per second towards the black 8 ball, which is at rest. Keep in mind that this 5 meters per second is completely horizontal. You're hitting it horizontally. And remember, this is a top-down view. So imagine you're looking from above a pool table at this scenario. And so you're going to hit the ball, and after the balls collide, you didn't hit it perfectly straight on. You hit it at an angle. And the 8 ball now goes that way at a speed of 3 meters per second, and let's say at an angle of 45 degrees. What I would like to know is what will be the velocity of the cue ball, the white ball, and I want both the magnitude and the direction. So in order to solve this, I'm again going to write my equation. P initial x equals P final x, and P initial y equals P final y. This is the initial scenario where it's just like the 5, and the final looks like that. Okay, great. So let's start with the x. That's easier. P initial x is mass times velocity, which for the white cue ball is 1 times 5. Just everything's positive too. That's not too bad. And then plus the momentum of the 8 ball, the black ball, which is at rest. So that momentum is just 0. Great. And then we said equal to P final x. Now, first of all, I need to find the x component of this 3 meters per second here, and that's going to involve drawing a right triangle here. So that's 45 degrees. This is 3, the hypotenuse, and I have my x and my y. Using the same logic we just did a minute ago with the triangle, x is going to be 3 times the cosine of 45 degrees, and y is going to be 3 times the sine of 45 degrees. And again, if you don't understand that, that's because cosine is adjacent over hypotenuse and sine is opposite over hypotenuse. So if I plug these in my calculator, for the x, I'm going to get 2.12. And since it's a 45 degree angle, there's a shortcut to find y. It's the exact same thing for a 45 degree angle. Now remember, this is my velocity, meters per second. So if I want to plug that in to my P final x equation, for the black ball specifically, I'm going to say mass, still 1. Velocity is 2.12. It's only the x component. It's not 3. And then plus the mass times velocity for the white cue ball, and that's going to be mass of 1 times its velocity, which is unknown, so I'm going to write Vx for right now. Yes, I have to write Vx because Vy, the y component of the white ball, is going to be different. So actually I can solve for Vx right now. It's going to be 5 equals 2.12 plus 1 times Vx. You just subtract 2.12. Looks like the x component of the cue ball is going to be 2.88 meters per second. And that's positive, which means that this cue ball, the white one, is still moving forward. So this is the x component. This is like half of my answer. To find the other half, the y component, I am going to have to set up P initial y equals P final y. And this one I think you're going to like, because look at the initial scenario again, this horizontal and everything. I would say that P initial in the y is 0 because there's no y component of velocity. That 5 meters per second is completely horizontal. There is no vertical component. V initial y is 0, so P initial is 0 for everything. Even the black 8 ball is not moving, so the initial is all 0 for the y component. Now the final in the y direction is not just going to be 0. It's going to be the mass and velocity of the black 8 ball, which is mass 1, velocity, we said was y component right here, 2.12. That's what I'll write right here. And then plus the mass times velocity of the cue ball. Mass is 1, velocity is what I'm solving for, Vy. Now I did make a mistake right now on purpose. I'm curious if you can see it. The thing that I did wrong is that velocity, 2.12, is incorrect. Look one more time at the picture. The black ball is not heading up, it's heading down in the y direction. So that means it should be negative 2.12 for the y. You have to be very careful of that in terms of the positives and negatives. Very easy to mess that up. So now I can solve for Vy. 0 equals negative 2.12 plus Vy. It looks like the y component is just going to be 2.12 meters per second. And that's positive, which means it's going up. Also, Vx was positive right here, which means it's moving to the right. So in other words, what this means is if I imagine my white cue ball, it means it's going to the right, 2.88 meters per second. It's going up 2.12 meters per second. And if I said I wanted to find both the magnitude and the direction, I want an angle and I want a hypotenuse. What I'm saying is I need to set up a right triangle again. So the x is 2.88, the y component is 2.12. This is my hypotenuse, which I'll call C, and this is angle theta, which I'll call theta. So let's solve for C first. That's just going to be Pythagorean theorem. A squared plus B squared equals C squared. So 2.88 squared plus 2.12 squared equals C squared. Let's plug the left side in my calculator. I'll get 12.79 equals C squared. And then we just take the square root of that, and we'll get 3.58 meters per second as the speed, the magnitude of velocity. That's the speed of the cue ball. And then if we want to find the angle theta, that's going to involve tangent. Why tangent? Well, because tangent theta of any angle is opposite over adjacent, and this is the opposite leg, and that's the adjacent leg, and I have both of those. So that means tangent theta equals 2.12 divided by 2.88, and then you just take the arctangent of that in our calculators, and we'll get our angle. So I plug this in my calculator, and I get an angle of theta equals 36.4 degrees. So I found my speed. It was 3.58 at an angle of 36.4 above the x-axis, like right there. Okay, so that's it for the first one. As you can see, conservation of momentum in 2 dimensions isn't that bad as long as you're good at the triangle stuff, which hopefully you are by now. I mean, it's probably halfway through the year. And now let's just look at one more question. Let's say we have an intersection here, a four-way stop. And I have a car here with mass M, and over here I have a big old truck, a 14-wheeler with mass 9M. In other words, it's 9 times heavier than the car. I'm not giving you what the mass is. I'm giving it to you in terms of M. Don't get discouraged when that happens. It usually just means the mass will cancel out. So what's happening here is the truck, the 9M, has the green light. So he's moving forward at about 5 meters per second. He's just picking up speed. And then the car doesn't see the red light at all because he's texting while driving. And he's heading through this intersection at 10 meters per second. And of course, they are going to collide. And after they collide, let's say that both masses together are now both moving at an unknown velocity at an unknown direction. And I want you to tell me both of those. So in order to solve this, again, you just need to say P initial x equals P final x. We'll do the x first. So look at the initial case. The initial case, only one of these cars is moving in the x direction, and that's the 9m. The m, the car, is just completely in the y, so that shouldn't even go in my P initial x. So P initial x, the mass is 9m. I don't care what m is, doesn't matter. And the velocity is 5, so times 5. And then that equals P final x, which is, this looks like a perfectly inelastic collision. Perfectly inelastic. And the reason why is because they stuck together. So what that basically means is for the final, I'm going to add the masses together. So 9m plus m times some final velocity vx. Again, I need to call it vx because it's the x component. So it looks like I get 9 times 5. For the left, I get 45m equals 9m plus m. That's going to be 10m times vx. Like I said before, the mass is going to cancel, as promised. Divide both sides by 10. Looks like my x component of velocity is 4.5 meters per second. Now I just need to do the same thing for the y. So P initial in the y equals P final for the y. Looking at the initial scenario, now the 9m, the truck, has no influence on the y direction because it was only x. The only thing that shows up in the y is the mass car because that is the only direction going in the y. And so the mass of that is m times its velocity is 10. Keep in mind that for all the numbers in this problem, I was very nice. Everything's positive because everything's moving to the right and upwards. If I chose any other direction, then at least one component would be negative, which is fine. It's not a big deal. But P initial y is just m times 10. That's it. P final y, again, perfectly inelastic. That means I add the masses together times some velocity vy. And so then I just say 10m equals 9m plus 10m, which is 10m vy. Looks like the 10 and the m both cancel, and vy is not going to be 0. It's going to be 1 meter per second. By the way, it looks like I did this intentionally, but I'll be honest, I make up all of my numbers on the spot, so this is just a miracle. And so now I have vy is 1 and vx is 4.5 meters per second. Again, we have to set up that right triangle where the x component is 4.5, the y component is positive 1, and I want theta and my hypotenuse c again. So same thing as before, 1 squared plus 4.5 squared equals c squared, and then I can just plug this in my calculator. So the left side will be 21.25, and the right side will just be c squared. Take the square root of that, and I get c equals 4.61, and that's going to be meters per second and the final speed of the system after the collision. And then if I want to find the angle, remember that we said it a minute ago, tangent theta equals opposite 1 over adjacent 4.5, and you just take the arc tangent of that, and I'll get a final angle theta of 12.5 degrees. So that wasn't so bad either, or at least I think so. So that's how we do conservation of momentum in 2 dimensions, x and y. If you have any questions, please post them in the comments below. Thank you all for watching, and I'll see you in the next video. Take care, and bye-bye.